in my last lecture, what I thought was I would talk a bit about statistical approach to analyzing linguistic sequences in a written form or analyzing inscriptions. Partly this will build on something that Rahul has already talked about. He did talk about Markov models. Well, I wouldn't say build on, it would basically amplify on what Rahul has said. So if you haven't completely got what Markov model is, I will again go over it, and I encourage you that if you have any questions, please ask. The reason why I'd like you to understand this fully is because it will form the base for what Nisha would be talking about tomorrow using n-grams to analyze the Indus script. So it's very important that you get at least a basic idea of what n-grams is all about. And essentially, the Markov modeling way of looking at linguistic sequences is going to give you this idea of what n-gram is. I will also talk about entropy. So this is Shannon's contribution, which Ashraf will be using when he talks about how to find direction in which a particular inscription is written using entirely sign statistics only. You don't even need to look at the material evidence. And finally, I'll be talking a bit about Zipf. And this has to do with, the frequency distribution of sign occurrences or sign cluster occurrences having a particular form. And again, this would form the base for what Ashraf would be talking about on the last day, where, he's doing this segmentation of long Indus sequences and trying to find clusters and see how these clusters actually, have a certain kind of distribution, which is very characteristic of language. All right. So this talk essentially will give you the basis for, looking at where the techniques that Nisha and Ashraf are using comes from, the basis of that. Okay, so, one of the things that often I encounter when I'm talking about Markov models is why look at a probabilistic way of how things happen, or why look at a statistical way of, looking at how language works? Purely, is language really statistical or probabilistic? Is probabilistic way the best way of looking at language? Well, as the Russian scientist Frankel once said, if a system is really complicated, then you must come up with a simple theoretical model for it. Because if you want to understand what's going on in a complex systems, it's no use trying to make your model also complicated, because that complexity is the first thing you want to understand anyway. So you have to simplify it, right? So one way to simplify it is to take a perspective of, or what we call a stochastic perspective, that is the perspective of looking at things as happening with probabilities, or in the most extreme case, looking at it as taking place randomly. Okay, so this is an approach which, among others, was pioneered by the Russian scientist Andrei Markov, where he kind of said that, look, you can think of how a particular system evolves over time as a probabilistic process. So the probability, each event. So let's say, you can consider your life as basically a series of probabilistic events. The fact that you went to a particular school, probabilistic event. The fact that you scored a particular marks in a certain class, probabilistic event. The fact that you went into humanities rather than science, occurred with a certain probability. The fact that you chose history rather than anthropology, again, you can assign a certain probability. So this entire life history can be seen as a probabilistic sequence of events. Of course, we are not denying that underlying those choices could have been, certain events. Let's say something happened to your family and you happen to be very mentally disturbed, and so you got very bad marks on a particular exam. And so as a result of getting that bad marks, let's say you didn't get, something. Okay? Or let's say you chose history rather than anthropology because, some point in your childhood, you came across a wonderfully interesting book on history, and that's what got you interested in history. But if you had instead like come across some book on anthropology, let's say one of Margaret Mead's books, you could have gone to anthropology instead. Okay, so we are not denying that there could be some actual deterministic events, but in absence of such knowledge, we are treating them as purely probabilistic events. All right. So that's the simplification we are doing. We are saying that we don't know all your life history. We don't know what exactly events transpired which made you choose this over this, or which made you, score well or score badly. So in absence of this detailed information, we are treating each event as a random event occurring with a certain probability. So that's the simplification. That's what Frankel would call making a caricature out of reality, in order to make it comprehensible, in order to make it possible to understand what's going on. So Markov said that you can model any process as a sequence of switching from one state to another state at each time step. Now, that might seem like, quite a complicated way of, saying what I just spoke about right now about your life history. But, think of the different choices you could have made when choosing a subject for your undergrad to be a number of possible states. Okay? So let's say subject 1, subject 2, subject 3, subject 4, subject 5, up to n subjects. So there were n possible states you could have adopted, and you chose one of them. So each choice you could have made, each of the subjects has a certain probability assigned to it. And with a certain probability, you chose history, or you chose anthropology, or let's say you chose computer science. All right. And then once you chose that, the next time step, let's say in your master's, you have to choose some specialization. So now if you are studying history, let's say you can choose ancient history or ancient Indian history, or, you can go for contemporary world history or whatever. Okay. So again, each of those specializations could mark a number of steps, and you are choosing any one of those states with a certain probability. So think of your entire life history as a sequence of choices, where the choices are being made between a number of discrete states. So that is how you can view your life history. And essentially Markov is saying that any time evolution, any process by which a system actually, changes from one time point to another, can be viewed as a sequence of such random choices made between a number of discrete possible states. Is that clear? Or if it's complicated, just let me know. Just think of the example I gave, your life history, and think how this applies. Okay. Now, some of you may be familiar with the idea of classical probability, right? So in classical probability, like for example, when we are tossing a coin, okay, so suppose I say, okay, what's the probability of, let's say I toss these 5 coins, and the probability that each of them will come up heads. So assuming these are fair coins, so the probability of coming up heads is half and probability of tails is half. What's the probability that all 5 will come up heads? Is that argument clear to everyone? If it's not clear to anyone, please don't feel ashamed. Just ask. Why should it be 1 by 32? Anyone wants to explain? You're given the answer, so maybe let someone else explain it. Anyone else?
Getting head once is half. So since we are flipping the coin say 5 times, so every time it will be 1 by 2, 5 times. That is 1 half to the power 5, which is what he said, 1 upon 32.
Exactly. Very good. Excellent. So although here I actually have 5 coins, right? So I'm assuming that each of them are fair. And when I toss this coin, okay, whether it comes up heads or tails doesn't affect what will happen with this coin. They're coming in 2 separate coins, right? It's independent. Even if they were not half, okay, let's say one coin was biased. So the probability of coming out heads was 2/3 instead of 1/3. But, so what will be the probability of having 2 heads? So let's say I'm tossing 2 coins. So let's take these 2 coins, okay? So let's say this is not a fair coin, okay? So the probability of coming up heads is actually 2/3. and probability of coming out tails is 1/3. Well, this is a fair coin. All right. So what is the probability that both will come up heads? Sorry? Why should it be 1/3? Both coming up heads. Plus, right. Okay. 2/3 into half. And so therefore 1/3. Fantastic. Yes. And I could do this because the coins, the probabilities are independent. If they were dependent, okay, so let's say all of these coins, both these coins were manufactured by the same factory using the same process. So both the heads, it turns out when I'm choosing the coin, I, take out the coins which have exactly the same biases. Okay. All right. And I don't know this, let's say. So then I'll end up with some correlation or dependence between these two properties, right? Okay. So one is this principle of independence, which means that now the joint probability of these two events, where the probability of A occurring is P and the probability of B occurring is Q, is actually the product of these two. And then the law of large numbers will apply so that you get finally the bell-shaped curve that we associate with probabilistic events. Several of you might have heard of this bell curve and so on. Now, in the Markov, you don't actually have these two, because what we are looking at are sequence of events where the probability of one event occurring is affecting the probability of the next, and so on. All right. So what do we mean? So essentially, in the Markov chain, you have a set of states and transitions between them, and the system is at any of these states at a given time. And over time, what is happening is the system is going from one state to another. Now, the only thing that you need to remember about Markov is, in the first order Markov process, in the simplest Markov process, what is going to happen in the future is just going to depend on what is going to happen, what is happening now. Okay? It doesn't happen on what is happening before present. So it only happens on what is happening now. So if you think of the current time to be t time, then immediate future is t plus 1. So what is happening going to t plus 1 is only dependent on what state you are in time t, and it doesn't depend on what is happening at t minus 1 or t minus 2 or t minus 3. In other words, going back to your life history example, if it's Markovian, it means whether you're going to take a certain specialization, ancient history or world history or so on, only depends upon, let's say, whether you chose history or something else. It does not depend upon what happened in class 10 or class 5. Okay. In reality, of course, this is not true, right? Often the events from our deep past can affect our decisions. But in the simplest Markovian assumption, your next decision only depends upon your current decision and no further back. Now, so this is an important thing to remember, that if you don't have memory, then the probability of each of this, for example, in the coin flip, so if you ask what is the outcome of the coin toss, so the probability of each flip is independent of the probability of the previous flips. In other words, I take this coin and let's say I toss it once and it comes out heads, and then I ask, okay, what's the probability that it will come out head next time? If it's a fair coin, what will the probability be that it will come out head? So same, it doesn't depend on the fact that it came out heads or tails, right? On the other hand, if I ask you, what is tomorrow's weather? Okay. Now, what do you think? What is tomorrow's weather going to be like? Very sunny, hot, right? It's kind of certainly not going to be snowy, right? Forget about it. So the fact, or even rainy for that matter, stormy, cloudy, and so on, is very unlikely, right? So here, clearly the weather tomorrow depends a bit on the weather today, okay? But need not necessarily depend on what it was 2 weeks or 4 weeks earlier, all right? So it depends on the immediate past only. Okay, so let's take a fun example. I mean, of course, coin tossing you might also consider to be fun, but let's take a funnier example. How many of you have played this game when you were a kid? Okay, quite a few. For those who haven't played this game, essentially it's a board game where you and a few other friends get together and you start with your tokens at this point. So this is the start of the game. And then you toss dice, and depending on what comes up, 1, 2, 3, 4, 5, 6, you move ahead so many steps. Okay. So you can see that, if you, for example, start from here, and let's say you get over here, income tax. So you have to end up paying. So each of you started with some paper money. So you have to pay a certain tax. On the other hand, if you get over here, so you toss us, let's say 1, 2, 3, 4, 5, then you get to have a chance to buy this particular railroad. So the whole idea is to buy up prime property like railroads or particular real estate and so on. But occasionally life gives you a lemon, so you end up with having to pay an income tax, or you could end up in jail, right? And so once you end up in jail, you have to miss a turn and then wait for the next turn and hope to get out of it and so on. Now, it's often said that this game of Monopoly is in some sense showing you the benefits of capitalism. Actually, if you look at the history, you'll find that the person who invented it, Lizzie Magie, had the entirely opposite purpose in mind. She wanted to show the ill effects of capitalism, in particular the greed of these landlords who used to rent out their buildings. But it's one of the ironies of capitalism that the game she originally invented to show the ills of capitalism was taken over by a company which then sold it very profitably. None of this profit ever came to Lizzie Magie. Okay, so they took it over and basically cut her out of it and reaped the profits. It became one of the most popular games. So quite unintentionally, she became a demonstration of the ill effects of capitalism, where the person who invents actually doesn't get any of the credit of the money. Okay, right. But the reason why we are looking at over here is to see it as an example of a Markov process. So suppose the game, you roll 2 die to decide how far to move. All right. So in that case, you can move. What is the smallest number of moves you can do? So what's the smallest number that will come up if you roll 2 die? 2, right? Because the first die comes of 1. Second die comes of 1. 1 plus 1 is 2. So the smallest move is you go this. So you can end up in this community chest. What's the largest move you can make? Longest move? 6 and 6 makes 12. So you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So you can go anywhere between this and this. Now, what are the possibilities? Okay. So the possibility that you will roll 1 with 1 die and 1 with the other die, what's the number of possibilities? 2. The first die can come up with, second die can come up with 1. But, so the possibility that you can have 1, 2 or 2, 1, and then 1, 3 or 2, 2 or 3, 1. So each of these, you can assign various ways in which these are possible. And so you can now, for this various possible moves from each of these squares, you can actually assign various probabilities. So the more possibilities there are, the more the probability that you will land up from here to these various squares, right? So the system has at least 40 states. Why 40? Because if you count the number of squares, you will see there are 40 squares. So these are the states. So at any point of time, you can be in any one of these 40 squares. So you say that the system has 40 states. Now, if you're in one particular state, you can move to any of these 11 possibilities. All right. So in other words, there are 11 transitions possible from each square. And since there are 40 states, there are 40 times 11 transitions between these states. Now, your fate depends on where you are on the board at present. Okay. So for example, if you are here, you can end up in any of these with certain probability, but the probability of you ending up from here directly to here is 0. Okay, so it only depends upon where you are currently. And it doesn't depend on where you were previously. So suppose you jump here. Now, once you jump here, then you are asking what's the probability that you will end up here, here, here. It doesn't depend that you came here from here. The past is completely irrelevant, right? And so fate depends only on where you are at present, and it does not depend on how you got there. Is that clear to everyone? All right. So that is a simple example of a Markov process. Now let's take slightly involved. So, 40 times 11 transition matrix is too complicated to think of. So I'll take something really simple. So this is a simple Markovian model of the weather. So let's say the weather can be in any one of 3 possible states. It could be sunny, as it's outside right now. It could be cloudy, or it could be rainy. Now, what are these arrows? So this arrow says that suppose today is sunny, what is the probability that tomorrow would be sunny also? So let's say that probability is 0.6. So, relatively high probability. But it could also be cloudy with some probability 0.3. And the probability that it could be rainy is only about 0.1. So there's only 1 in 10 chance that if today is sunny, tomorrow would be rainy. Okay, but the chance is not 0. All right. Similarly, if it's cloudy today, what's the probability that it will be cloudy tomorrow? 0.3. What's the probability that it will be sunny? 0.2. And what's the probability that it will be rainy? 0.5. So, if today is cloudy, the highest probability is that tomorrow would be rainy. But, with medium probability it will be cloudy, and with a small probability it could be sunny. And if it's rainy, then with high probability it would be rainy again tomorrow. But there is also, like a relatively high probability that it will be sunny. So it will be sunny with probability 0.4. And it's cloudy. Tomorrow will be cloudy with probability 0.1. Is this diagram clear to everyone? If it's not clear, just ask. Because this is in some sense what's going to set us up for understanding Markov process. Is this clear? How this is explaining some kind of a very simple model of weather? Now you might say, where will I get the probabilities from? Any ideas? How will I actually get these probabilities? Sorry? One is you simply look at history, right? So what has happened in the past? Okay, so you look at your entire weather series data and you ask, okay, if let's say day T was rainy, how many times it was sunny, how many times it was cloudy, how many times it was rainy. So you just take a ratio and that will give you kind of a relative frequency. So that's one way to assign probabilities. Of course, you could assign it by pure imagination, but that's not going to be very useful. Okay, so you use, in fact, that is where actually the learning part comes in. Okay, so people often talk about Markov models and, learning models and so on. The learning comes in the fact that, where these probabilities actually are coming from. So you learn these probabilities. All right, so is this clear to everyone? All right, can I take it as a yes? Okay, good. So now this starts looking more mathematical, right? But actually it's no different from what I wrote here. Okay, basically this table is just showing that if it was sunny today, what's the probability that it will be sunny tomorrow? 0.6. If it's sunny today, what's the probability that it will be cloudy tomorrow? 0.3. And if it's sunny today, what will be rainy tomorrow? 0.1. And similarly, if it's cloudy today, what is the probability that it will be cloudy today, and so on. All right. Now, from this, using a little bit of algebra, you can actually work out what would be, So what is the probability that it will rain in 2 days if it's cloudy today? How do you do that? Well, you do it like this. So you said, okay, it's cloudy today. All right. Now, it could be in any of these states, sunny, cloudy, rainy. Okay. But what I want to know is what the weather would be like day after tomorrow. Okay, not tomorrow itself, day after tomorrow. How do I do that? So I ask, okay, I can go from cloudy to sunny and then that sunny to rainy. Okay, that's one way I can get rainy day the day after tomorrow. or I can go from cloudy to cloudy and cloudy to rainy. So that's how another way it will be rainy on day 2. And then finally, cloudy to rainy and rainy to rainy. So that's 3 possibilities. Okay, so let me just, in case that's not clear, let me just write this down. So cloudy today. So what the Markov matrix is giving me is what will it be tomorrow. So if it is sunny, if it is cloudy, or is it rainy? All right. So then what are these properties? Can anyone help me? It's kind of hard to stare it over here. Can you tell me what's the probability that it will be sunny tomorrow? 0.2. What's the probability that it will be cloudy tomorrow? And rainy tomorrow? 0.5. Very good. Okay. Now, what do I want day after tomorrow? Rainy, right? All right. So what's the probability that if it's sunny today, it will be rainy tomorrow? Sunny today, rainy tomorrow. Yeah, 0.1. Correct. Cloudy today, rainy tomorrow? 0.5. And rainy today, rainy tomorrow? 0.5. Excellent. Okay. And now, what's the net probability of this? 0.2 into 0.1, right? So I can rub this out and say that the overall probability is 0.2. What's the probability of this? Sorry? Sorry? Oh, sorry. Yeah. You're right. Correct. And this one? 0.25. Okay. So now I notice that, okay, so why is it coming out different? Sorry. 0.2 into 0.1 plus 0.3 into 0.5 plus 0.5 into 0.5. Oh, okay. So I just need to take the sum, right? So, so I take the sum. What will I get? So 0.25 plus 0.15 gives me, sorry, 0.4. 0.4 plus 0.02? 0.42. So the probability that if it is cloudy today, it will be rainy day after tomorrow is 0.4. So here, what is the underlying assumption? The fact that only the weather the day before matters. So here, I could multiply these two numbers simply because I'm saying that, okay, the probability that it will be rainy day after tomorrow only depends upon what it was like tomorrow. Doesn't matter on what it was the day before that, that is today. So tomorrow depends on today, day after tomorrow depends on tomorrow, the day after tomorrow depends only on day after tomorrow, and so on. And this is what allows me to multiply up these probabilities and get the final number. If that condition is violated, then you get a higher order Markov process. So this is basically the simplest of the first order Markov process. Okay, so in this way, I can now not only do a 1-day forecast, I can do a 2-day forecast, 3-day forecast, 4-day forecast, and so on, right? So if you keep doing this, so basically what I'm doing is I'm basically taking that the table of numbers and multiplying it with itself, okay, to basically find out what the different probabilities would be. So if I okay, so let me just see. Yeah. So if I just take each of these numbers, okay, and start multiplying with itself. So if you are familiar with matrix, Are all of you familiar with matrix? Is there anyone who is not familiar with matrix? Okay. So essentially, this is a table of numbers, and there is a particular rule in how you multiply a table of numbers with another table of numbers. So essentially, you do this kind of a thing. You take each row and multiply it with each column such that the first element of this row is multiplied with the first element of this column plus, and then you add it to the second element of the row multiplied with the second element of the column, and the third element of the row multiplied with the third element of the column. You add them up, and that gives you the first entry of that table of products. Okay, so that's a very, very, very simple rule once you get to know it. And when you are essentially multiplying this table with itself, it means that basically you are taking a square of this matrix, and this will become just 0.6 square, then and so on and so forth, right? So you get, sorry, I made a mistake. It should be 0.6 times 0.6 plus 0.3 times 0.2 plus 0.1 times 0.4. That sum will give you this entry over here. So that is essentially what you are seeing over here, okay, after getting it. So this is basically the matrix multiplied with itself. Sorry, this is the matrix multiplied with itself. This is the original Markov matrix, which just gives you what's going to be the weather tomorrow. So this is what's the weather going to be after 2 days, which is obtained by multiplying the table of numbers with itself. And this is obtained, so this is the 3-day forecast. So this tells you what the weather would be like the day after tomorrow. So what you do is you multiply the matrix with itself and then again multiply it with itself. So you raise it to the power 3. You take what is known as a cube. So in this way, if you keep doing it, you notice something very funny. After a while, the table of numbers don't change much. Okay. So it's going to converge to a given set of numbers where it's going to be 0.44, where it's going to be 0.44 for sunny, 0.235 for cloudy, and 0.324 for rainy. Okay. Regardless of whether 7 days before you had sunny, rainy, or cloudy. What does that tell you? If you go far enough into the future, then what is happening today is no longer affecting it. So these probabilities that you see is simply the proportion of sunny days, cloudy days, and rainy days you have in your time series. If you just look at how many sunny days were there, how many rainy days there were, how many cloudy days were there, your data actually had exactly this proportion. There were 44% sunny days, 23% cloudy days, 32% rainy days. Okay? So if you go far enough into the future, then your information about present is no longer going to tell you anything very useful in the first order Markov process. It's only going to tell you what you have in the data. That in the data you have this many proportion of X, this many proportion of Y, this many proportion of Z, the different states. Is that clear? Okay, good. Now, why did I go into this example? I mean, after all, this is a workshop on epigraphy and not on meteorology. That's because then Markov went on to apply this to works of literature. In particular, he used Pushkin's famous long poem, a novel written in form of a poem, Eugene Onegin. And what he did was, he took basically, lines of Pushkin and said that, look, if I know what is the probability that a particular letter will follow another letter, if I basically, just obtain by simple calculation that what's the probability that this letter will follow this letter. So given that there are 26 letters, we ignored the capitals and small letters and stop basically where the word boundary is located. So if you only take 27 symbols, then we have a table of numbers. How large? What would be the size of the table of numbers? What will be the order of the matrix? So I have to look at 27 symbols following 27 symbols. So it will be 27 by 27. Is that clear? So essentially each entry of that table is giving me what's the probability that A would be followed by A, or A will be followed by B, A will be followed by C, and so on. Okay. So in this way I have a 27 by 27 table, and then I worked out the probability of each of this A followed by A followed by B, just calculating it from the poem. How many times is A followed A? How many times is A followed B? How many times is A followed by space, for example? Okay. So that's what he did. And so now, let's say you have this fragment of text. So let's say he was too young to have been blighted. So you just take this particular fragment of text without any punctuation or spaces. So it just becomes was too young to have been blighted. And then you basically work out what's the probability of vowels and consonants. So you find out that there are 7,788 vowels and 12,212 consonant occurrences. So the probability of you take any particular letter from this, the probability that it will be a vowel is about 0.4 or 40%. Probability that it will be a vowel, consonant is about 60%. But the really interesting part is here. So you're asking, what's the probability that a vowel will follow a vowel? Okay. So you find that there are 1,300 examples, 3,060 examples of that. And similarly, vowel followed by consonant is about 6,000. Consonant followed by vowel is 6,000. And consonant followed by consonant is about 5,700. So this gives you a transition matrix. So vowel followed by vowel, with a probability of 0.175. Vowel followed by a consonant is 0.825. A consonant followed by a vowel is 0.526, and a consonant followed by a consonant is 0.474. So that already tells you that a vowel-vowel pair is actually very rare compared to, let's say, a consonant-consonant pair or a consonant-vowel or a vowel-consonant combination. Okay. But that's not all. So now what you do is you take the simple Markov model where you just work out what is the probability. So, you take that 27 by 27 matrix, where what you do is basically just have probabilities that A follows B, A follows B, A follows C, ... A follows space. B follows A, B follows B, and so on. And now, starting from some arbitrary letter, you just use this matrix to generate a piece of text. So you start with A, let's say, and then you find out, okay, what is the probability of A being followed by A being followed by B? So you draw a random number from a computer, and then according to that number you draw, you figure out whether it's going to be A, B, C, D, E, F. Some of you may not have a good idea of how this works. Does everyone know how you will use a random number generator to do this? No. Okay. So, you know that even if you take a simple calculator, sometimes the simple calculators would have a rand function. So you press it and out will pop a number between 0 and 1. Okay. So that's a random number generator. I mean, how you generate it, we won't go into this. There are many algorithms. Let's assume that they are truly random. Okay. So you let's say get 0.426. Now, suppose the probability of having, so I will demonstrate it with just 3 letters, or maybe with just vowels and consonants, because doing it with a 27 by 27 is very complex. So what did we have? 0.175, 0.825, 0.526, 0.474. Okay. So this is present. This is future. Okay. Now, let's say I take a consonant. I begin with a consonant. Okay. Now, what is the probability that the consonant would be followed by, hold on a sec, something not quite right. Yeah. So what's the probability that the consonant will be followed by a vowel? It's 0.526. What's the probability that it will be followed by consonant? It's 0.474. Now, if you notice these two sum to 1. So the total probability should always be 1. Now, so basically this says V followed by V plus, sorry, C followed by V and C followed by C, this should equal 1. Now, how do I work out whether this should be, in my particular example, B or C? So what do? I use my random number generator. Now, what a random number generator does is that with uniform probability, so this is a number, let's say, with uniform probability, it will generate a number between 0 and 1. Okay. Now, suppose I say I put a barrier mark at this point 526. Now, what is the probability that the number I generate using a random number generator would be less than this number? What is the probability that the number that I generate using the random number generator would be less than 0.526? Remember, it's uniform probability. Sorry? Is it 1 minus or is it just 0.526? It's just 0.526, right? Because if you look at this section, okay, it is proportional to 0.526, right? So the probability of this is simply 0.526. And what's the probability that it will be greater than that? It's 1 minus. So it's 0.474. Okay. That's because the probability of getting any number less than 0.526 is a constant and it has to sum up. If you sum up, the total probability that you got a number less than 0.526 is basically the sum of this area. Now we know that the sum of this area plus the sum of the area is equal to 1, and the ratio of proportionality between these two areas is 0.526 to 0.474. And so this obviously has to be the probability of 0.526. So now it becomes very simple, right? So I will simply generate a random number and I will ask, is that number less than 0.526 or greater than 0.526? Okay. So I'm asking the question, is the number obtained from my random number generator less than 0.526? There are only two possible answers, right? Yes, no. Okay. So the probability of this is 0.526 and the probability of this is 0.474. Now, what is the corresponding 5 to 6 probability? It's consonant followed by a vowel. So if I get a number less than 0.526, I would put a vowel, and if the thing is greater than 0.526, I get a consonant. So I just pull up my calculator, punch the random number generator machine, and let's say I get the number 0.13452,897. Your calculator is 8-digit calculator, let's say. So what will my answer be? Is it going to be vowel or consonant? Vowel, right? So I get a vowel. Okay. Now once I get a vowel, I have to switch to this row, right? Because now I'm starting with a vowel. Okay. So what is the probability that vowel would be followed by a vowel? 0.175. And what is the probability that vowel will be followed by a consonant? 0.825. So again, then I have now a similar random number generator where if I put the bar over here, okay, actually I can even put 0.175, it doesn't matter. I can put the bar at 0.175. So what's the probability that I'll have a number less than this? 0.175, right? Because it's completely proportional. And the probability of this, that it will fall on this area, is 0.825. Okay. So I ask, is the random number less than 0.175? Yes, no. Okay. So the probability of this, as we already know, is 0.175, and the probability of this is 0.825. Okay. So if it is 0.175, what will it be? Vowel, right? Consonant. Okay. So then I punch my random number generator once more, and let's say this time around, the number that I get is 0.66638012. So what will it be? Sorry? Consonant, right? And so the next will be a consonant. And now I switch over here again. Okay. And now I already know, right, what to do. I will again punch my random number generator, and this time round, the number that I get is like 0.3642890. So what will I get? Vowel. And in this way, I can now start generating an entire sequence of consonant, vowels, and so on. So I did it with 2 just to show you the simple case, but you can now do it with these 27 symbols corresponding to A to Z and space. Okay. And so now, if you do that, this is what you will get. Doesn't look like anything meaningful. Okay. But whatever you did with first order, you can also do with second order. That means now what is going to happen in the future not only depends on what is happening in the present, but the immediate past. Okay. So it will not only depend upon whether it is vowel in the current thing, but whether there was a vowel or a consonant in the immediate preceding thing. So it's a second order Markov. And similarly, you can do a third order Markov and so on. So once you go to third order Markov, you see that it starts making, it looks like a surreal poem. At one is snowfall, make a stick to us. It sounds like something from Rupi Kaur, right? So, is Olga's up? Okay. Sounds like a very avant-garde poem. Right? At fifth order, already you start seeing that, meanwhile with jealousy bench, and so it was his time, but she tricked, let message me visits at date, and so on. Parts of it almost seem like, grammatically correct. And all the words are at least English, right? And by seventh order, my sorrow abreast over the dumb torment of a whale. I mean, this actually sounds like poetry. I don't know about you. This does sound like poetry to me. Okay. All right. So you see where the power of Markov process comes from. Okay. This is not my work. This is the work of Brian Hayes, who used to write this computer recreations column in Scientific American. And but I've seen other people, try this out, and they say with a very, very high likelihood, as you increase the order, you start getting things which look English. But be aware that if you start increasing the order even further, eventually at some point it just gives you back what you trained it on. You don't get anything novel. So there's a optimal number of the order which you can use. But yeah, I mean, characteristically, there's some intermediate order at which you start getting, on average, almost like English constructions. Okay, any questions so far? All right. So this is exactly also the work that Shannon did, and which Rahul in his talk actually mentioned briefly. So Shannon actually did essentially the same thing. And he also found that as he went to higher and higher orders, it went from something which looks a complete random assortment of letters to something which almost seems like English. And this work was, of course, done decades after Markov's work. So Markov's work actually dates from 1913, whereas Shannon was, I think, doing this sometime in the 1960s. Okay. Now, Shannon actually used this to also predict English text. Okay. So he said that, look, sometimes we can actually predict very accurately a piece of text even when we have a lot of missing information. So let's say this was the original piece, and let's say, you are, like, let's say, taking out these particular letters. You would still, with very high likelihood, be able to work out what it is, or maybe this, because essentially we have a lot of implicit knowledge of, words and how they're put together. So even if you take out a lot of things, you should still be able to predict. And so he's basically pointing out that there's a lot of redundancy in natural human languages. We don't really need those pieces of information, but we still have it. Okay. Now you might ask why. Why do we have, if we could just figure out from this very short piece of text that I mean polished wood but less on the shabby red carpet, why do we have this additional letters? And that's because to protect against noise. Because whenever we are communicating, there's a lot of ambiguity, there's a lot of error which creeps in, and you would like to make sure that your message gets across without major corruption. And that's why we have lots of redundancy built into natural languages. So this is essentially what is used by, your phone when it does autocorrection. So most of the time, we are extremely irritated by autocorrect because we are typing something and we mean something, but, it thinks we actually mean something else and it will type, and you hit it, go before realizing that you actually typed wrong things. And then you have to apologize. Sorry, I didn't mean this. It's Google's autocorrect.
So the current example that you showed, it works on the probability of the next character. So how do you estimate, how do you break the word? So when do you know to break a word?
Yeah. So as I said, I was using 27 symbols. 27. What is a 27 symbol? It's space.
It's space. Yeah.
Yeah. So that's how I break.
That probability is also calculated in this.
Yeah. So that is how I break the word. So I say, what is the likelihood that A will be followed by space, B will be followed by space, and so on.
All right.
And similarly, what's the probability that space would be followed by A, space would be followed by B, space would be followed by C, and so on. Okay. Now, it's good that you mentioned this word level, because Shannon not only did at the character level, Shannon also did at the word level.
Mm-hmm.
Okay. So he said, what's the probability that this word will be followed by this word? Now, that becomes a horrendous exercise because, unlike characters where you can just work with a 27 by 27 matrix, for words, you'll have to work with 10,000 by 10,000, or, even if you look at the most commonest words in English, you have to work with something like order of 10,000 by 10,000 matrices, right? So it becomes a very complicated exercise, which is why I didn't show that example. But yes, whatever I did with characters, you can do with words. Yeah. And in fact, as Nisha would point out, in Indus, we don't even know whether they're words, letters, or what they are. Are they syllables? We have no clue, but you can still apply Markov. And we can do something like autocorrect. I don't think you mentioned that in your paper as autocorrect, but it is effectively autocorrect. Yeah. Right. So in autocorrect, essentially this is what you're doing. You start with something and then basically figure out like, okay, if you start with I, so what's the probability that it's going to be followed by am or do? Okay. Or let's say love. Okay. So you follow these probabilities. So if basically from an analysis of a large number of previous sentences, Google has decided that this is the highest probability, it will suggest am. And then with a certain lower probability, it will suggest do or love. Okay. So in this way, you can follow like, I am only human after all. Or you can say, I am so tired. Or you can say, I do love you all. Okay. Or I do love and hate apple or banana, and so on. So these are all possible strings that you can generate simply by following these probabilities. Okay. Right. And for those who are in love with this game, okay, this is this actually shows you just how much strong correlation there are between letters in a given word, which is why we can actually solve it. If each of these letters were occurring independent of the others, there's no way we can solve a wordle by just 6 attempts. We can solve it simply because, in 6 attempts, simply because once we can guess a letter correctly, or once we can guess that a letter is somewhere in a given word, it constrains the number of possible choices enormously. Okay? So without, if there was no correlations, we would, in the worst case, require, so each of these places could have 26 letters, right? So it's 26 times 26 times 26 times 26 times 26. So that's 26 to the power 5, which is 10 million, right? So if there were no correlations, we would require about 10 million guesses in the worst possible case, unless, of course, we are lucky and we managed to guess it in the first case. But, of course, most of these are not valid English words. Okay. So in reality, it will be a lot less. And even then, it would not have been enough. But the fact that, often, if you have a consonant, it will be very likely followed by a vowel. Or if it's a vowel, almost definitely will be followed by a consonant, gives you a enormous restriction on what can follow. And that's why you can do it in most of the time in 6 cases. Okay, so it's 1 o'clock and I'm completely out of time. I wanted to talk a bit about Shannon, but if I keep going, I think I will completely swamp lunchtime. So maybe I will stop here, and I think it's heavy duty enough. If we find time somewhere at some other point of time, I will then maybe Ashraf. Where is Ashraf? Yeah, Ashraf, can I steal some of your time? Okay. So Ashraf doesn't have an option of saying no, right? Okay, so maybe I'll steal some of your time and just introduce this, because hopefully it will help in your talks. All right. So any questions?
The summation of all the probabilities will always be 1 in the a Markov case.
No, so summation over all the possible transitions. So basically what you're saying is, so suppose you look at all these possibilities. Say, we, say, we say. Okay. So what's the probability that I'll have a CV combination, CC combination, VV combination, or VC combination? This is not the same as what's the probability that V will be. So this is not the same as these numbers. Okay. Why? Because this is basically tell you that if I know V, what's the probability that the next character would be V? Whereas what I'm saying over here, what is the probability that I'll get a CV pair? Okay. How will I work that out? Can you guess?
You have VV pair and you have
so this number, so you might think that, okay, this is probability of VV.
Yeah.
Okay. But I'm saying that, notice what this is. This is saying that if I have a V, what is the probability that the next character is V? Okay. So it's slightly different. Realize? Okay. So what's the probability that I'll have a VV? So first I need to work out what's the probability that I'll have a V in the first place. Okay. How do I find that? By basically doing this iteration many, many times, because I know when I multiply the matrix with itself over many times, eventually it will come to this overall probability distribution of just V's and C's. How many V's are there? How many C's are there? This number. This probability. So the probability of that you chose a V in the first place was 0.389. Times, what's the probability that since it was a V, you had after that a V? That is this number. Okay. So the probability that it will be VV is basically 0.389 times 0.175. What's the probability that it will be CC? It will be 0.611 times 0.474. Okay, and so on. So then you'll have 4 such pairs, right? So it will be 0.389 times 0.175 plus 0.389 times 0.825 plus 0.611 times 0.526 plus 0.611 times 0.474, and that will equal 1. Because those are all the possible two letter combinations that there can.
And sir, one more thing is isn't this approach quite data oriented? So suppose if a new letter comes to a dictionary, so we have to add it to our empirical data, and the probabilities will change. So over n iterations, won't our final output will be, the final probabilities will be very much different from the previous ones, or will it be similar?
So what you say is actually very relevant when we are dealing with ancient inscriptions, because as I mentioned, if I have a finite, so I always have a finite corpus, depending on how much I dig. Okay, so I've dug up and found 700 seals, and from this I basically find that there are, let's say, 600 odd distinct symbols. Okay, now tomorrow somebody digs at another place, finds another seal which is a new character. Okay, and then I have to incorporate this into my model. And so you're saying that how much would my previous results change as a result of all this? Now, interestingly, the fact that I already have hundreds of seals and this new letter that I found is only available in this additional seal already means that this is a very rare symbol. So the occurrence probability is extremely low. And as far as I know, because in a given inscription, let's say it has occurred only once. So in the entire corpus, it has occurred only once. And that new inscription which I found in which it occurs once only and next to a particular symbol. Okay. Now, what does that mean? It means in that entire Markov matrix, which is now becoming, let's say, it was previously, let's say, 600 by 600. Now it has become 601 by 601. Okay. But that means most of the entries on that 600 first column and 600 first row are actually 0. Okay. There's only one entry which is actually a finite number, and that too is a very, very small number. Okay. Now, people will, that is not the end of the story. So if this was the case, then you will say that, oh, okay, that means it won't change much, which is true. But now, people will say, hold on a second. The fact that you found this means that this character actually occurs in some other inscriptions which have not yet been found. So how can I say that, the probability that it follows any other letter is 0? It may be I haven't found those inscriptions. I can't just put 0 by default. Okay. So there are, statistical estimator methods called Turing-Good estimation method, where they put a very, very small number. They don't put 0. They put a very small number. And basically, as and when more data comes in, they start correcting it. Okay. So you should not put 0. You should just put a small number in order to do this calculations.
How small should be that?
So that is given by the Turing-Good estimation method. So this is a very, very relevant question you asked. Thank you for asking it. In ancient inscription, this problem turns up again and again and again, because most of the time we have no clue whether we have the entire corpus or not.
Thank you.
Any other questions?
Say example, the letter Z. We know that it occurs very rarely and the probability will be very low. And we may say that, okay, it's kind of irrelevant character. But couldn't it also be the other way, that when it occurs, it's an important character?
Could you give an example?
Yeah, I meant something like, say for example, in the terms of ancient history, the seal of a king, for example, it occurs very rarely. Maybe, I don't know, probably wrong. For example, let's assume comes very rarely.
Yeah.
But it's an important seal, right? But for example, accounting terms, it occurs very frequently. Right. Which in terms of context seems very irrelevant, right? It's just accounting numbers. But if you look at it, it's a king seal. It's a very prominent seal.
Okay, so I'm not sure I completely understood your question, but maybe this is what you're asking. You're saying that suppose I find a particular symbol occurring with high frequency, how do I know that it's not in some very restricted context? How do I know that actually this frequency with which I'm getting it is the frequency with which it occurs in general? I might have just chanced upon a particular archive with a very specialized purpose where it happens to occur with high frequency. Is that the question you're asking?
Yeah, essentially. Huh.
Yeah. So, these issues are always there. So, for example, in another context, I can tell you, like, suppose you dig up an archaeological site and you find a bunch of skeletons and they're all 6 feet tall. Okay. Now, can I argue, they have some height, which is a mean of about 6 feet. Now, can I argue on the basis of this one grave site alone that the people of this culture were very well nourished because they all had tall heights? It could be just the elite grave, right?
Yeah, exactly.
It's a king's grave. So this issue of sampling bias would always be there.
Yeah.
But one trick you can do, and this is a method which was actually very used very frequently in statistics, is called bootstrapping, which is when you have a restricted sample and you want to know that how representative is the sample of the unknown population. You can do something like this. You can pretend that the sample itself is the population and do random sampling from the population. Okay, and then ask, can I say something about the sample from the subsampling that I've done from the sample itself, treating the sample as a population and the subsampling that I'm doing from it as the sample. So how representative is the sample I got from the originally unknown population? So this bootstrapping is something we do very, very regularly in, for example, our linguistic databases. Because always we are dealing with, certain pieces of text. Okay? And that may be all the text that we have ever found of this culture. So how do we know that this is a representative sample? So one way is to do this bootstrap sampling. Okay, pretend that the sample is the population, and then if we had done a random sampling, would be able to say something about that sample. If we can't do that, that means it's not a very reliable sampling. So that's one of the tricks we do. But sampling bias is always there, unfortunately. You can do some things to try to correct for it, but hopefully that kind of answers the question. Yeah.
And we are trying to measure term frequency. They also have, instead of just measuring the frequency in which each term occurs, they also have TF, IDF, where they assign weight to the terms that occur rarely. So more weight will be given to terms that occur rarely than words that occur frequently. And so in that case where TF, IDF is used, first of all, I don't know in what context. So term frequency, inverse document frequency.
Okay.
Yeah, where it's like a weighted frequency measure where more weight is given to rare words. I don't know first where that would be useful, but if that is the case where you would have to use it, then their question would be relevant. So how do you factor, combine that kind of a statistical method with this?
Okay, so I don't know exactly where, this kind of an inverse frequency is used. Typically, whenever we find rare signs, we try to work out whether there's any particular context with which it is correlated. So suppose we find a rare Indus sign, and we also find that it only occurs in, let's say, Mohenjo-daro. Or let's say it only occurs in copper implements and not in seals. Okay, so that gives us some clue that it might be some context specificity which makes this sign only occurring here. So for all we know, it might be actually an allogram. That is, it might be actually representative of another character, which because of the context is written differently in these two seals. So sometimes the similarity of these signs might give us a clue that it's actually the same sign. So for example, you would see that in the Indus database, there are two signs, this and this, that look very similar. Question is, do we treat them as different signs or do we treat them as just sign variants? So it could be that if you're inscribing it, then because when you're etching something on metal, it's much easier to do straight lines. That's why you'll get like this. But using a curving tool, when you're curving a seal, it might be easier to do this kind of a curve. So it might be just the stylistic variation which comes about because of the writing method or on what you're writing. But it could also actually have different meanings. So the context often actually tells us that how, whether with high likelihood is this a variant or is this distinct characters. Now, same arguments can be applied to very rare sign occurrences. Could a rare sign be occurring only, let's say, in, some metallic implements, which could be used for a ritual purpose? So is it like writing Om? So these are the kinds of arguments we sometimes try to use, but I don't know any particular context in which this inverse frequency is used. So I'll be happy, if you can give me further details. I'll just look it up and see what is the context.